Welcome! In this session, we'll tackle LeetCode problem number 1726, tuple with same product. This problem challenges us to count all tuples where the product of two numbers equals the product of another two numbers, with all elements being distinct. Let's explore the problem together and break it down step by step. In this problem, we are given an array of distinct positive integers called nums. Our task is to determine the number of tuples, a, b, c, d, such that the product of the first two elements, *b, is equal to the product of the last two elements, c*d. Additionally, all four elements must be distinct. It's important to note that tuples are considered the same if their elements are rearrangements of each other. For example, a, b, c, d, c, d, a, b, and b, a, d, c are all considered identical. The input is an array of numbers, and the output is the total count of such valid tuples. Let's look at an example to understand this better. For the first example, where nums equals 2, 3, 4, 6, the output is 8 because there are 8 valid tuples. These tuples include 2, 6, 3, 4, since 2*6 is equal to 3*4, as well as its permutations like 2, 6, 4, 3, and 6, 2, 3, 4. Each of these tuples satisfies the condition that the product of the first pair equals the product of the second pair, and all elements are distinct. Since we account for all possible rearrangements, we have 8 tuples in total for this example. Now, consider the second example, where nums equals 1, 2, 4, 5, 10. The output here is 16 because there are more combinations of numbers that satisfy the condition. For instance, 1, 10, 2, 5 is valid because 1*10 is equal to 2*5. Similarly, 2, 5, 1, 10, and its permutations also work. In total, we find 16 such tuples where the product condition holds true, and all elements in each tuple are distinct. Finally, in the third example, nums equals 2, 3, 4, 6, 8, 12, the output is 40. This is because there are many valid combinations that meet the condition, such as 2, 12, 3, 8, and its permutations. The problem also comes with additional constraints. For example, the length of nums is between 2 and 100, and each number in nums is a distinct positive integer between 1 and 10,000. Edge cases include scenarios where nums has fewer than 4 elements, meaning no valid tuples are possible, or cases where no two products match, resulting in 0 valid tuples. Additionally, the problem challenges us to handle large inputs efficiently within the given constraints. To tackle the problem tuple with same product, we aim to count all unique tuples, a, b, c, d, where the product of one pair equals the product of another pair, and all elements in the tuple are distinct. A straightforward way to approach this is by brute force. The intuition behind this method is simple. We generate all possible combinations of 4 numbers from the array and check if the product condition holds. This involves using 4 nested loops, iterating through every possible tuple, and verifying if the product of one pair equals the product of the other pair. While this method is conceptually simple and easy to implement, it has a major drawback. The time complexity is n to the power of 4, where n is the size of the array, making it computationally impractical for larger datasets. Additionally, the space complexity is 1, but the sheer number of operations makes this approach infeasible for real-world applications. To address the inefficiency of brute force, we turn to an optimized approach using a hash map. Instead of explicitly iterating over all possible tuples, we can leverage a hash map to store the products of pairs, enabling us to efficiently check for matches. Here's the key insight: if a product, say P, is shared among multiple pairs, then we can group these pairs together in the hash map. For each product, if there are k pairs that produce it, we can calculate the number of valid tuples using the formula k*k1/2, which comes from combinatorics. To implement this, we first iterate through all pairs in the array, compute their product, and store the pairs in the hash map under the corresponding product key. Once the hash map is populated, we compute the total number of valid tuples for each product and multiply this count by 8, as each tuple can be permuted in 8 distinct ways. This approach eliminates the need to explicitly generate all combinations, thereby significantly reducing computation time. The time complexity of the optimized hash map approach is n², as we compute the product for all pairs in the array. The space complexity is also O n squared, since we need to store these products and the associated pairs in the hash map. While the space usage increases compared to brute force, the time savings are substantial, making this approach far more scalable. By grouping pairs with the same product, we avoid redundant calculations and streamline the process of counting valid tuples. This efficiency is why we chose the hash map approach. It improves the time complexity from O n to the power of 4 to O n squared, which is a dramatic improvement for larger input sizes. Moreover, the space complexity is manageable given typical problem constraints, such as arrays with up to 1,000 elements. By leveraging the relationship between pairs and their products, we can solve the problem in a way that balances speed and memory usage effectively. The brute force approach, while simple to understand, is impractical for large inputs due to its O n to the power of 4 time complexity. On the other hand, the hash map approach offers a clear advantage in terms of efficiency and scalability. By pre-computing and grouping pairs with the same product, we achieve a significant reduction in computation time. Alternatives, such as sorting the array and using a two-pointer technique, are less efficient because they do not utilize the hash map's ability to group pairs by product. Another option, using a frequency array, lacks the flexibility required to handle distinct elements effectively. The hash map approach strikes the right balance, optimizing both time and space complexity. It is conceptually straightforward and well suited for the problem constraints, making it the ideal choice for solving this problem efficiently. The problem tuple with same product requires us to count all unique tuples, A, B, and C, D, such that the product of the first two numbers equals the product of the second two numbers, and all four numbers are distinct. Given an array of integers, our task is to find an efficient way to solve this. The core idea is to group pairs of numbers that produce the same product. Once we have those groups, we can calculate how many valid tuples can be formed from them. To achieve this, we use a hash map where the key is the product of two numbers, and the value represents the pairs that produce this product. This strategy allows us to efficiently manage the grouping process and count tuples without directly iterating over all combinations of four elements, which would be computationally expensive. For example, if the array is 2, 4, 6, 8, we can compute the products of all pairs of numbers, 2 * 4 equals 8, 2 * 6 equals 12, 2 * 8 equals 16, and so on. These pairs are grouped in a hash map, where each product serves as a key and the associated pairs are stored as values. To construct this data structure, we iterate through all unique pairs of numbers using nested loops. For each pair, we calculate their product and add the pair to the hash map under the corresponding product key. Once this grouping is complete, we can focus on counting valid tuples. For each group of pairs with the same product, we determine how many ways we can select two pairs to form a tuple and use a formula to calculate the total number of permutations of these four distinct elements. To finalize the count, we iterate over each product group in the hash map. For each group, we calculate the number of tuples using the formula 4 * k choose 2, where k is the number of pairs in the group. This formula accounts for both the selection of two pairs and the permutations of the four elements within the tuples. The key insight here is that grouping pairs by their product drastically reduces the complexity of the problem. Instead of checking all possible combinations of four numbers, which would take O n to the power of 4 time, we only need to generate pairs, which takes O n squared time. This approach leverages the hash map to efficiently organize and retrieve information, and the combinatorial formula avoids the overhead of explicitly generating tuples. Together, these techniques make the algorithm highly efficient. Now, let's look at the implementation. First, we initialize a hash map to store the product groups. As we iterate through all pairs of numbers in the array, we calculate the product and increment the count for that product in the hash map. Once the grouping is done, we traverse the hash map to count tuples. For each product group with more than one pair, we use the formula 4 * count * count 1 / 2 to compute the total number of tuples. Here, the combination formula, count * count 1 / 2, determines how many ways we can select two pairs, and the multiplier 4 accounts for the permutations of the four distinct numbers within each tuple. Finally, we sum up the counts for all product groups and return the result. This implementation is efficient, with a time complexity of O n squared, for both the pair generation and the counting process, and a space complexity of n squared, in the worst case for storing the hash map. There are a few edge cases and optimizations to consider. If the input array has fewer than 4 elements, no tuples can be formed, so we immediately return 0. If the array contains duplicate numbers, the algorithm naturally handles this by grouping pairs based solely on their products. For large input values, we rely on Python's ability to handle arbitrarily large integers to avoid overflow issues. To optimize memory usage, instead of storing explicit pairs in the hash map, we can store only the counts of pairs for each product. Additionally, if a product group contains only one pair, we can skip its processing entirely, as no tuples can be formed from a single pair. These optimizations ensure that the algorithm runs efficiently and scales well for larger inputs. This implementation solves the LeetCode problem tuple with same product using an efficient approach. Here is the breakdown of the code, step by step. 1. Imports *. We use default dict from Python's collections module to handle the mapping of products to their occurrence counts. This allows us to efficiently count the number of pairs that produce each product. 2. Initialization *. A dictionary product _to _count is initialized to store the number of pairs that produce a given product. The variable result is initialized to 0 to store the total count of valid tuples. 3. Nested loops *. The outer loop iterates through the indices of the input list nums. The inner loop iterates over all indices greater than the current index in the outer loop. This ensures that we only consider pairs, nums, I, nums, j, or I less than j, avoiding redundant computations. For product calculation * for each pair, nums, I, nums, j, the product of nums, I, * nums, j, is calculated. This product is the key for grouping pairs that share the same product. 5. Tuple contribution *. If there are already pairs that produce the same product, stored in product _to _count, for each existing pair, 8 new valid tuples can be formed. Therefore, we add product _to _count, product, *8 to the result. The factor 8 accounts for the permutations of the 4 elements in the tuple. 6. Update product count *. After adding the contribution to the result, we increment the count of the current product in product _to _count by 1. 7. Return result *. After all pairs have been processed, the final value of result is returned, representing the total number of valid tuples where A*b equals C*d and all elements are distinct. This approach efficiently handles the problem by grouping pairs with the same product and avoiding the need to explicitly generate all possible tuples. The time complexity is approximately n squared, where n is the length of the array, as we iterate through all pairs of numbers in the nested loops. This is the Java implementation for LeetCode problem number 1726, tuple with same product. The logic mirrors the Python implementation, where we use a hash map to track the frequency of products of pairs. The result is calculated by summing contributions based on existing counts in the map and multiplying by 8, as each pair contributes to multiple valid tuples. Key differences include Java's explicit type declarations, the use of hashmap instead of Python's default dict, and handling default values for missing keys using getOrDefault. This implementation effectively maintains the same functionality while adhering to Java's syntax and conventions. In this problem, we aim to find the number of unique tuples, A, B, C, D, such that the product of A and B equals the product of C and D. The elements of the tuple are distinct, and the order of elements in the tuple matters, meaning permutations of the same elements are considered different tuples. For instance, given the array nums equals 2, 3, 4, 6, we start by initializing a dictionary product _to _count to keep track of the frequency of products we encounter, and a variable result to store the total number of tuples. Initially, both product _to _count and result are empty or 0, respectively. Next, we iterate through all pairs of numbers in the array using nested loops. For the first outer loop iteration where I equals 0 and nums, I equals 2, we calculate the product for every subsequent pair. For j equals 1 and nums, j equals 3, the product is 2 * 3 equals 6. Since this product is not yet in product _to _count, no tuples contribute to the result. We then update the dictionary to include this product, setting product _to _count 6 equals 1. Continuing with the same outer loop iteration where I equals 0 and nums, I equals 2, we move to the next inner loop step. For j equals 2 and nums, j equals 4, the product is 2 asterisk 4 equals 8. Again, since 8 is not in product underscore to underscore count, it does not contribute to the result. We update the dictionary to include this product, resulting in product underscore to underscore count equals 6, 1, 8, 1. For the next pair where j equals 3 and nums, j equals 6, the product is 2 asterisk 6 equals 12. Similarly, 12 is not yet in the dictionary, so it does not contribute to the result. We update the dictionary to include this product, resulting in product underscore to underscore count equals 6, 1, 8, 1, 12, 1. Moving to the second outer loop iteration where I equals 1 and nums, I equals 3, we again compute the product for subsequent pairs. For j equals 2 and nums, j equals 4, the product is 3 asterisk 4 equals 12. This time, 12 is already in product underscore to underscore count, with a count of 1. This means we can form a matching tuple, and we add 1 asterisk 8 equals 8 to the result. We then update product underscore to underscore count, 12, to reflect this new occurrence, resulting in product underscore to underscore count equals 6, 1, 8, 1, 12, 2. Still in the second outer loop iteration where I equals 1 and nums, I equals 3, we compute the product for the next pair. For j equals 3 and nums, j equals 6, the product is 3 asterisk 6 equals 18. Since 18 is not yet in product underscore to underscore count, it does not contribute to the result. We update the dictionary to include this product, resulting in product underscore to underscore count equals 6, 1, 8, 1, 12, 2, 18, 1. Now, in the third outer loop iteration where I equals 2 and nums, I equals 4, we compute the product for the final pair. For j equals 3 and nums, j equals 6, the product is 4 asterisk 6 equals 24. Once again, since 24 is not in the dictionary, it does not contribute to the result. We update the dictionary to include this product, resulting in product underscore to underscore count equals 6, 1, 8, 1, 12, 2, 18, 1, 24, 1. After all iterations are complete, the final value of result is 8, which represents the total number of valid tuples, A, B, C, D, where the products of pairs match. Now, let's consider another example with nums equals 1, 2, 4, 5, 10. As before, we initialize product underscore to underscore count as an empty dictionary and result equals 0. We iterate through all pairs of numbers in the array to compute their products and update the dictionary. Whenever we encounter a product already in product underscore to underscore count, we add to the result based on the count of that product. For instance, when the product is 20, derived from pairs like 2, 10, and 4, 5, we find matches that contribute 8 to the result for each occurrence. These matches occur because the same product can be formed by different pairs, and each match allows for 8 permutations of A, B, C, D. After processing all pairs, the final value of result is 16, which reflects the total number of valid tuples for this input array. Finally, let's examine the case where nums equals 1, 1, 1, 1. As before, we initialize product underscore to underscore count and result to empty or 0, respectively. Since all numbers are 1, the product of any pair is always 1. Each time we compute a product of 1, the dictionary product underscore to underscore count is updated, and result accumulates based on the frequency of the product. Because all pairs yield the same product, the count of tuples grows rapidly as more pairs are processed. Ultimately, the final value of result is 96, which corresponds to all possible permutations of valid tuples, A, B, C, D. This example demonstrates the efficiency of the algorithm in handling cases where products repeat frequently, leveraging the dictionary to count matches and avoid redundant calculations. When analyzing the time complexity of this solution, we start by examining the nested loops. The outer loop runs from the first element to the second to last element in the array, which results in n iterations if the size of the array is n. For each iteration of the outer loop, the inner loop starts from the next element and runs to the end of the array. This means the inner loop executes fewer iterations as the outer loop progresses, resulting in a total of n*(n1/2) iterations overall. This is because we are essentially selecting pairs of elements, and the combination formula accounts for this. Inside these loops, the operations performed calculating the product, updating the dictionary, and computing intermediate results are all constant time, or O1. Since the nested loops dominate the number of operations, the total time complexity of the solution is O(n squared). Now, considering the space complexity, the primary factor is the product_to_count dictionary. This dictionary tracks the frequency of unique products formed by pairs of numbers from the array. In the worst case, every pair of numbers produces a unique product, leading to O(n squared) entries in the dictionary. However, in practical scenarios, products often repeat, so the actual space usage can be less. Apart from the dictionary, the algorithm only uses a few variables like result and loop variables, which require constant space, or O1. Therefore, the overall space complexity is dominated by the dictionary, with a worst-case complexity of O(n squared). Comparing this optimized approach to a brute force solution highlights the significant improvement in efficiency. A naive approach would involve iterating through all possible quadruples, A, B, C, D, to check if A*B equals C*D. This would lead to a time complexity of O(n to the power of 4, since there are that many combinations of 4 elements in an array of size n. Additionally, the brute force approach does not require extra data structures, so its space complexity would be O1. The optimized solution, on the other hand, reduces the time complexity to O(n squared by focusing on pairs, A, B, and leveraging the product_to_count dictionary for efficient counting. While the dictionary does introduce a possible O(n squared) space complexity in the worst case, this trade-off is well worth the drastic improvement in runtime. In both the best and average cases, the time complexity remains O(n squared due to the necessity of iterating over all pairs, and the space complexity depends on how many unique products are generated. To mathematically confirm the time complexity, consider how the nested loops iterate over all unique pairs, I, j, where I less than j. The total number of such pairs is given by the combination formula, Cn2, which equals n*n1/2. This simplifies to O(n squared in asymptotic terms. Within each iteration of the loop, the operations calculating the product, accessing the dictionary, and updating its values are all constant time, or O1. Therefore, the overall time complexity of the algorithm is dominated by the O(n squared iterations of the loops, confirming that the algorithm indeed has a time complexity of O(n squared). When solving this problem, there are several common mistakes to watch out for. One major issue is failing to consider all unique tuples. Remember, the numbers A, B, C, and D must be distinct, so using the same pair on both sides of the product equation violates the constraints. Another mistake is relying on a brute force approach, which involves iterating over all possible combinations of 4 numbers. This results in a time complexity of O(n to the power of 4, which is impractical for larger inputs and will likely exceed time limits. Additionally, when using a hash map to track products, it's easy to mishandle multiplicity. If you don't carefully count and update the product frequencies, you might end up undercounting or overcounting valid tuples. Edge cases are another area where errors arise. Arrays with fewer than 4 elements or those containing duplicates can lead to runtime errors or incorrect results if not handled properly. Finally, some misinterpret the formula for counting tuples based on product frequencies. For example, applying the wrong combination formula can lead to incorrect calculations, so it's essential to derive and apply it correctly. To succeed in interviews, understanding the key patterns behind this problem is crucial. The main insight is recognizing that the problem reduces to finding pairs of numbers that share the same product. A hash map can be used to store the frequency of each product as you iterate through the array. This allows you to efficiently track these pairs. Optimizing the solution is also important. Instead of examining all possible quadruples, which is computationally expensive, you can focus on pairwise comparisons, reducing the time complexity to O(n squared). Additionally, it's important to clarify constraints with your interviewer. For instance, ask about the presence of duplicates or the maximum array size to ensure your solution handles edge cases properly. Be ready to explain the trade-offs between a hashmap-based solution and a brute force approach. The hashmap method is faster but requires additional space, so discussing these trade-offs demonstrates your understanding of both time and space complexity. This problem is related to several other problems, which can help you think about variations and alternative approaches. For example, LeetCode 454, for sum 2, involves a similar hashmap-based approach but focuses on counting tuples with a target sum. LeetCode 15, 3 sum, emphasizes finding unique triplets that sum to 0, showcasing pairwise combination techniques. LeetCode 18, for sum, focuses on generating quadruples with specific sums, which is slightly different but shares some conceptual overlap. Lastly, LeetCode 1, 2 sum, introduces the hash map technique for pair-based problems, which is a foundational concept for this type of problem. When considering alternative approaches, brute force is the simplest, where you generate all possible quadruples and check if their products match. However, it's highly inefficient with a time complexity of n to the power of 4, making it unsuitable for larger arrays. A more efficient approach involves using a hash map. By iterating through all pairs, calculating their products, and storing them, you can count valid combinations using a formula for combinations. This optimized approach reduces the time complexity significantly to n squared, though it does require additional space. Another alternative approach involves sorting the array and using a two-pointer technique to identify pairs with the same product. While less common for this specific problem, this method can be useful in certain variations. The trade-off here is that sorting introduces an n log n overhead, and the implementation can be more complex compared to the hash map-based solution. However, in some cases, this approach might provide a more intuitive way to think about the problem, especially if sorting helps to simplify the pair selection process. Ultimately, the choice of approach depends on the given constraints and the specific variations of the problem you're solving. Great job! We've successfully solved tuple with same product and learned how to use hash maps effectively for counting relationships. Keep practicing similar problems to strengthen your skills, and don't forget to subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!